It's more fun. We've got Rob and Dan here who's going to talk about CubeSat. And Dennis knows a lot more about these guys than I do, but I'm going to let them introduce themselves and start their presentation here.
A few moments later.
Same things happened with CubeSats, probably back in 2010-ish, 11-ish. Oh, we have a presentation, okay. I was just talking to buy time. Okay, so anyhow, CubeSat is a small satellite, but you don't need big ones anymore. Well, you do for certain things, but for a lot of tasks that they're accomplishing, they don't need to have a big satellite. They could be a little satellite. Now, CubeSat is very small, a little bigger than a softball, but microelectronics, right? Micro thrusters and micro this and that. Matter of fact, NASA had sent 2 CubeSats to Mars. Anybody hear about that? Marco 1, at least I got one head nod on that. That's not Marco 1.
That's a CubeSat, though.
Yeah, Marco 1 was about 6 times that size. They link them together like Legos, and it made it all the way to Mars on probably xenon thrusters, once they got it going in the right direction and everything. So anyhow, it's, I call it thinking inside the box, because this is about not just CubeSats, but CubeSats in STEM. Just like the computer revolution, it hit the schools pretty hard. Remember that? The school teachers just about went crazy over the things. Okay, students did too. I did too. So next, you go. Should I have the mouse? And I can just next it.
There you go.
Okay. So I'm trying to say it's kind of like a mini equivalent revolution of the PC revolution. And here's the different sizes, what constitutes a CubeSat. Big one would be probably the size of that table right there, maybe 3 times that size, But 10 centimeters cubed is called a 1U, okay? And you stack 2 of them high, you got a 2U, 3 high, 3U, and so on. And the one that went to Mars was a 6U. They stacked those 6 little Legos together. Probably a lot of it was fuel. Usually the maximum weight is approximately 4 kilograms. So it's got limits to what you can define. Now the reason they keep it at that is because they are launched by other services, such as a rocket from another country. They load these things up in some spring-loaded compartment and then shoot them out one after another. And the guys that invented it, 99, I can't pronounce that one guy's name. It's Jordy, I got that part. Pugid, sorry? Anybody know foreign names real good here? Help you out? Bob Twiggs, I like that. People just need to keep it simple. So anyhow, they wanted to have something that their students could get their budget around and their hands around and build in the classroom there. You can see they're holding these 2 small CubeSats. So, Manners University, California Polytech State, and Stanford. Okay, so up to date, there's been 2,300 CubeSats launched. There's probably more than that. Okay, typical altitude, now this is rough guessing, I think I did this off the top of my head, probably much lower. They probably go up as low as 150 kilometers. Never much higher than 500. There are exceptions to the rules. A new one from the AMSAT is going to be called Gulf. Okay, greater orbit, larger footprint. Anybody heard of that one? Yeah. It's higher you go, the longer it takes to go across the horizon, the more amateur radio guys can lock on a signal and do stuff with it, right? That's the big advantage. It's going to have other goodies in there too, but that's amateur satellite. We're really about the CubeSat itself here. So. And this is what the classroom thing. Kids love it. I mean, why do people love CubeSats? I mean, I don't have to be convinced too much. They're very interested. Tonight there's a speaker about CubeSats. What's that? Reminds me of the whole PC thing all over again. But it's not going to be as big. It could be the awe and mystery of space, Star Trek, Final Frontier, a positive future, mining asteroids, right? Having robots and people go out to those things, creating colonies and bringing back valuable materials that we need. Mind-challenging technology. The robot revolution kind of came and went, right? I mean, that's the little robots, and they had robot wars. You're going to be able to do a lot with robots in space. Matter of fact, you should be doing more with robots than people on some of these distant missions. It's 1/1,000,000th of the cost. Okay, and relative newness is something new and exciting, right? CubeSat, satellite technology. So, mystery of awe of space. It's like when you see a shooting star, this is kind of a ethereal, but if you know who that is, that's Jeff Naukin, Meteorite Men. To grab something and touch something that's been a star in space. When I was a little kid, my dad used to make me lean my head against the house and look up and watch the satellites come over. Anyone ever, well, now it's Elon Musk, they're swarming over, right? But, to think that little bitty star that was man-made, back in the 60s, that was really impressive. But it still got that attitude of grabbing a meteorite. Why you know, that there's an attitude there about space. Positive frontiers, you know, talking about mining, things like that. Obviously, you get involved with space in general. This is an open door. They're not going to give you well, there might be some geniuses in the room here that are going to get down to Cape Canaveral and inherit a spaceship or something. But overall, the only way you're going to get your hand on space is CubeSat. Mind-challenging technology. So you can finally use your ESP32 modules, your ham radio skills, in order to build something in a group. And it's not that. It can be hard, but it's so interesting. It drags your brain forward, even if you're stupid like me. Potential interest from USA schools alone. Now, high schools in America, these are public high schools. There's 27,000. How many of those kids do you think would be interested in this kind of CubeSat that they could have on their desk and do something that was going to go in space?
7.
Yeah. Okay. Cost of going to space. This is going to shock you. A lot of articles still are behind. They say 40,000 or 100,000 to get your CubeSat up. Not anymore. Not India. As low as 10,000. There's this big wig in charge. I don't know if I got Symantec. I'm very bad with names and the foreign ones. Samanath, right? I'll go with that. He's the head of this ISRO. It's Indian. That's their NASA, if you want to call it that. But they're talking about 10,000 to 15. But I've seen recently he wants to get down to 5,000 a launch. You know, you almost could do it here at PCARS, right? Get the Treasury budget up and there's a problem with that, isn't there? Has anyone been thinking about this problem? You know, 27,000 high schools. That's just the high schools. One high school, one launch per year. Where are you going to be at? And then a new wave of students come in after that, and they want their satellite up there. So that's not feasible, is it? What are we going to do about it? I saw a solution once on Star Trek, and I think it's going to work. Do you remember that one?
Oh, yeah.
The planetary eater. It digests the satellite, and then it makes itself longer, and then eats more satellites, and then nobody can stop it, right? Okay, realistic solutions. You know, they're going to start not giving you granted license to launch if you don't have a way of destroying the darn thing after a year or two. So there's different methods of doing that. One is to have a little deployable parachute. Usually what they have is a spring-loaded system, and they got a little fire wire, kind of like the wire that used to have on Estes rocket, and they burn that, called a burn wire, and out come the springs, and then you get a little parachute. Hit more air molecules up there, because there's always some, and eventually drag you down into a decaying orbit. Deploy at low orbits. If you go nice and low, statistically, you'll be brought down, but then you're at the mercy of the sun. Because a couple solar flares, the atmosphere does swell a little bit, and you'll come roaring in after a month. The drag system I showed you, and small propulsion systems. That's going to be a big, big thing in the future. It's going to open new doors. Remember, there were things. Does anyone know who Lance Ginner is? Does that ring a bell with anybody? First Oscar satellite. You know, who would have thought in the mid-40s or even early 50s that amateur radio guys would be putting a satellite into space? Wasn't that incredible? So it happened. You know, and what I'm saying, dare you think forward without getting laughed out of the house? What could happen in the next 20, 30, 40 years with small spacecraft? And I don't know if you're familiar with xenon propulsion. They have amazing things going on. I don't have all night to go into xenon, but it's $100,000 for a lecture bottle, so that's a roadblock on xenon propulsion. Okay. Still, there are ways that teachers and students that want to have their hands on space, you know, have some space tech experience, piece of the future. There's a way to do it for everybody. And I think Dr. Alan B. Johnston of AMSAT, he's the vice president of educational outreach, and he has, I think it's kind of been handed to him like a baton, but they have this thing called the CubeSat simulator. Okay, and what it is basically a mock satellite. I think in theory it could fly. They usually radiation harden them and vacuum test them, but I remember a long, long time ago in QST magazine where they had launched a Kenwood with a solar panel strapped to it. Does anybody remember that? Or I'm the only one that thought I saw it. I think, yeah, like 89 or something, 92. Little solar panels on there. You know, kind of gets into a quandary here. What they do is they send the data out of the device through the solar panels. It's called housekeeping. How's the battery doing? How the solar panel's doing? You can tell how fast it's tumbling, right? Once it starts spinning up there, it's very hard to get it to stop spinning unless you have some counteracting force. But it sends that down. Here's the signal of it. I just did a screen capture. You usually get a perfect eye out of this thing. I'll try to get a live demo out of it. Let's see. And there's the boards inside. He's coming out with a new set of boards. There's the batteries. You know, I really kind of frown when I see NiCad batteries like that, but I guess they use them a lot in the space. Lithium has trouble with temperature cycling. So it gets pretty cold in space. Unless you have a way of not getting cold with the other side of Earth, you're going to be in trouble. So they use other kind of batteries like that, but that's what they use on a lot of CubeSats. I would prefer lithium if possible. Those other sensors up here are each attached to the solar panels, and it lets you know the health of each one. Is it working? Is it, how much energy is it bringing in at the time? Are you rotating? Because if you're not rotating, only 1 or 2 sensors are going to work. The other one's called the STEM board. Now, I frown on it a little bit. Great accomplishment. This guy's a pioneer, so all due respect. But it's a little Amazon module. It was a BME 380, 280, something like that. 280. They're about, what, $4 a piece? You get the blue ones. Those type of modules bring in temperature, humidity, and pressure. Now, can anybody guess what those values are going to be at 250 kilometers? You know, temperature might be interesting, but after that, I think humidity is going to be dead zero. So, you know, they just want data to send, and that's their problem. That's what they just want, and that's what put a bug in my ear. Now, here's the sensors they do have on them right now, and the telemetry they'll come across. Somebody's passing around the CubeSat. That's Johnson's. What's his first name? Alan B. Johnson, Dr. Alan B. Johnson. That's his unit being passed around. Okay, pressure, temperature, humidity, some MEMS, so if it's tilting, you can, I don't know if that would work in a zero microgravity environment unless it's going really fast. You know, GPS, I think you want to use a GNSS or whatever it's called, because at a certain altitude, GPS gets kind of funny, right? You get up to the kilometers. Slow scan TV in there. Now, that's not invalid at all, because you have a bandwidth issue if you're at low power and you got weak signal. These things usually go at 100 milliwatts. Sometimes you're lucky a watt, right? But in that kind of power range, you're not going to get much signal. And that's what they do to Mars, basically. They send very slow, low bandwidth. You know, I'm going like that. I'm seeing the streams of data coming across the screen, right? And they have to wait. I think how long they have to wait to get all those movies, that little helicopter cruising around, right? It's a slow thing. So if you want to go far, you're going to have to lower your bandwidth, you know. And the power unit, the batteries, things like that, CPU temperature. I almost forgot to put this in the slideshow, so I should have put a picture in it. They're powered, and I'm powered by the Raspberry Pi 2W. Anybody knows what that is? A 2W, Raspberry Pi users in here? Cool little tool. I'm very surprised. The first one was a real dog, right? The first one was, I don't know how much memory they have. I think they have 4 gig on them now. So a lot of times I want to say 4 megabytes because I'm still living in the past. But anyhow, they use the phase lock loop output pin, and they can actually get a wide range of frequencies on there. Right now, that thing that you're passing around is going at 434.9-ish, and it works rather well. I think it's about 100 milliwatts. Anybody know? So. And then they have added a UHF transceiver module because it's going to have repeater capabilities. A lot of CubeSats, even university ones, tend to throw a chip like that in there so they can be also used as a repeater contacts as it goes around. Not enough of those, actually. But anyhow, there's the telemetry. You get the eye of the signal right there when you tune it in right, and the data telemetry starts flowing, and then it starts filling up these values. I think, no, they actually got some values in there. I was just doing screen captures, so whatever I had at the time. Okay, to help mature the CubeSat, we're developing our own thing called OmniSat. The reason we call it OmniSat is because it has anything you want to throw in there. You know, it's got some different technology, more stimulating technology. This is the first circuit board. We're actually in our prototype phase. I mean, this is not a polished product yet. Some things are just proof of concept, or someday we'll do it. A lot of stuff we have done, though, and there's our muon detector, so it's got a cosmic ray detector built into it. That takes a lot of space. You actually have to use 2 of those because when a muon comes in, cosmic ray, it can penetrate a lot of stuff. It's not like a gamma particle or an alpha particle, but it can shoot right through. So what you do is you have 2 scintillating detectors, and it lights them up, and if they both go off relatively at the same time, that means that was a very hard radiation particle. It plowed its way through both of them. That's usually done from a cosmic ray shower. as the particles. A muon, by the way, is like a heavy electron. Well, it was thousands of times heavier, but it's got a charge and spin similar to an electron, I believe. So we got that. Yale University puts this exact same type of technology. This is our own circuit board, but it's open source. You can redesign it the way you want. Yale put one up, and they're all happy about it because they put their muon detector in space. Muon detector. Okay, so did I just say that wrong? Huh.
You labeled it wrong.
I see that now.
Right.
That one's right.
That's wrong.
That's the stem board.
No, that's
The
wrong.
power board? Yeah, power supply. I can't see very well. Where am I missing one? There's supposed to be 3 of them.
Stem.
There's the stem board. Okay. And a lot of times they put a little Arduino module on there, but we have a whole stem compartment just for the muon detector, and I'll pass that around so you can see that. It's actually got a little display on it and everything. When both of them go off at once, you know you got a muon, put it that way. Hardware and software compatible with the CubeSat sim that AMSat has. We got the same signals and things like that we can put in and out. Physical improvements. I don't know where the little one went. Can anybody hold that up, that little one? Let's see where it went. That's the authentic CubeSat sim. Okay, and I didn't put any solar panels on that one. They want you to put them on with sticky tape. And right now, I sound like a hypocrite because mine are stuck on with sticky tape, but mine's a temporary prototype. Once I make sure they're all working, I'll put them on with epoxy, okay? So I knock the sticky tape, and then I end up getting caught because one of the panels falls off tonight while I pass it around with sticky tape on it. But that's what their final product is, and there's no way to open it up to look at the insides. People are that impressed, and they've gotten very successful with that thing covered in solar panels. And it looks like a glass box, and it's that magic star, and the schools go wild over it. To me, that's not enough. You got to be able to open up. You want to stand up and show them under the lid there? You know, I don't have a slack on that one.
Yeah, you're kind of plugged in up the way.
Okay.
You're set up here.
But you can open mine up, and you can flip open the panels. Eventually, when I get more developed on this, I'm going to make it so the panels stick out and stay out. You know, it's kind of not at that phase yet, but they open up and you can inspect it. So that's a big improvement in my mind, is robust solar panels too. He's only got a couple, I've got 4, because I'm right now making this for a 2U unit, right, 2 stacked high, and eventually a 3U unit. I don't know if I'll get pretty flappy with those solar panels after a while. So easy access inside, we can go, you know, whatever, how many U's we want to Lego set the thing together in, snap them together to more pieces of equipment, more things. It's got a GUI interface where I can get into VNC. Everybody knows what VNC is, desktop sharing, and I can run commands immediately, whereas they have this shell thing, and Raspberry Pi people love that shell thing. I hate it. I like to see a nice, easy-to-use GUI interface. What's it called? SSH, Secure Shell? The kids know, right? What does that stand for? I'm never going to use it, so I don't know why I bother memorizing it. I hate it. I just whip VNC in there, and off I go. You know what I'm saying? I use terminal after that. Scientific sensors. There may be spelling errors in this because I was up late last night putting this together. The cosmic ray detector. I'm going to eventually probably put alpha, beta, gamma detector in there. A magnetometer. No, that's got an issue because you really want that thing to spring out and be in front of the spacecraft, not embedded. But, you know, this is just a STEM thing. That'd be a lot of work. But anyhow, amateur spectroscopy. That one. Too bad Chuck Cole didn't show up tonight, did he? He loves that kind of stuff. We are working on a unit right now where it can actually look at the sun, possibly stars, and then download what elements it's seeing if it could get focused. And that's way off, but we have a desktop, what is it called? Proof of concept. We're still building that. But there's, again, the cosmic ray detector. There's 2 of these units stacked high inside the unit there. It's the 2U unit. And the cosmic muon is a byproduct of the cosmic ray. Those usually come from neutron stars crashing each other, black holes crashing each other, known as particle showers. They probably have a, 5-kilometer diameter on average. And look at you, see if you remember it. But it has to go through both of these chunks of plastic that are wrapped up in electrical tape and whatnot. I think I'm pouring some kind of black goop over it, look a little better. But if they both count at the same time and they're hooked together, it's called a coincidence event. And that means, hey, something went through both those big chunks of plastic. And gamma could, but not ionizing stuff like a muon detector would. Attitude control and determination. Any satellite NASA type people in here that are familiar with that? Attitude control and determination? No? Okay. Well, you know, we're talking about a CubeSat. You throw that out of one of those boxes with a spring load, and what's it going to do? It's going to tumble. What does Newton's laws say? It's going to keep tumbling until acted on by another imbalanced force. So you got a problem with that. So anyhow, there's a set of tools you can use. A solar sensor, because I don't have one yet, but it's easy to make. It's just a cross, 3D printed cross. And we'll get to that. Reaction wheels, a magnetorquer, that's a really cool thing, and micro thrusters. I'll cover each one of these for you. Okay, there it is, 3D printed, and you have little silicon detectors there, and it detects the shadow so you know if you're pointing at the sun. You know, you have no way of, if you're going to do something about the tumbling and try to stop it, you have to know where you are, right? Just stopping it wouldn't help you. So that's a very important part in the rear end of the satellite. Then there's something called a reaction wheel, and that's another proof of concept, work in progress, but they're really cool, so I'm sure we won't have a problem whipping that together. What they do is they spin like the bicycle, right? And you know, in physics class, right, you had a bicycle and you'd hold on to it and the teacher would tell you to try to turn it. It's really hard to turn, right, because it's spinning. Okay, they use a series of those wheels to change the inertial momentum of the satellite, and it can be tilted any way you want it if you know where you are. So a combination of the solar sensor and the reaction wheels, you can actually steer it to point, like if you have, ours has a camera, if you want to point down and look at the Earth, that'd be nice, instead of just black and 3 stars, right? Then you use the reaction wheels to determine it. And that, you know, that's something to talk about STEM. You know, when you use a reaction wheel, you're doing that bicycle experiment in a much more interesting way than just the bicycle wheel, right? You think they're getting you ready to work at a bike shop the rest of your life. Put that in your hands. But you're also getting to this multiple wheels and trying to orientate yourself based on data coming in from that sensor. And that gets into some really sophisticated mathematics. I think, what was it called? Eigenvectors. Okay, and you got to do those on the fly. You just got done taking a course and it was hard, right?
No, I didn't have a course on that.
The doctor,
But
we did it just for fun, huh?
Yeah.
Eigenvectors, yeah. Okay. Usually it's one of the more advanced, I'd say first year graduate electrical engineering. Anybody have eigenvectors, eigenvalues? There we go. It wasn't that easy, right?
No.
And to do it, yeah.
Why not a little gyroscope?
Well, that's kind of what they're doing in a way. But there are 3 or 4 of them because you got to balance it to where you want it to tilt. You know, because otherwise you got to tilt the gyroscope, right? You know, so they have different wheels that spin up and spin down. It can get into some kind of thing called gimbal lock. Okay, you got to figure out how to break out of that. Remember Apollo 13 with Jim Lovell? We got gimbal lock. I remember those words coming across. So you have to way of breaking out of it. And this is the device that might just help you do that besides a thruster. This is called a magnetotorquer. And you just talk about STEM. What this thing does is it uses the Earth's magnetic field with those bar magnets, if you want to call them that. They're on a rod just like an AM radio antenna. And that sits there and charges up with computer control to use the Earth's magnetic field to help it get realigned. And I think that's very cool. So, and it's just full of STEM. I mean, you can imagine where this is going to go with STEM, right? I mean, when I was in school, here's a compass, there's a magnet, or how about we pour powder on some paper and you put a magnet underneath it and it'll make this neat pattern, right? This goes a little further, doesn't it? It gives them a hands-on, hey mom, I want to go home, buy some Arduinos and wrap some magnetorquers on my own. Now, what we're going to try to do with this thing, with both the reaction wheel and magnetorquer, is when we finish the next phase of it, I mean, we just cram this puppy together. But we want to hang it from the ceiling on a fishing swivel, horizontally, and then have the thing turn with a remote control to demonstrate these principles. You know, we're not going to have the 4 wheels that they usually have. We'll probably have 1. But it'll be able to turn its direction left and right on that swivel. And we also have some other cool technology that's going to do that. And the magnetorquer might work fine with the swivel also to turn its attitude. This is the neat thing now. We've done this proof of concept. We're going to pass it around. Don't let them plug the battery in. How many volts is that?
20,000.
20,000 volts. That might stop your heart. So anyhow, plasma thrusters, and there's so many more of these than, you know, micro thrusters are probably a better topic, right? I can see certain faces light up when I talk about those things. So anyhow, that's just a plasma thruster. It just actually uses air, which is cheating. You should have a gas like xenon or argon or something. Remember, the xenon is $100,000 for a lecture bottle about this big for liquid xenon. But you can get argon a lot cheaper, $5,000 or something. But we have atmospheric air, so it just sits there and pushes. It makes the thrust out of the atmospheric air with the electric field that arcs across there. And so that's an official thruster. We're going to have like 2 of them, I think. I think I'll have 2 fake ones and 2 real ones, because when we're hanging from the ceiling, we're only going to be able to turn left and right. You know what I'm saying? Not up and down. And these things, you know, that's the modern propulsion system of choice. If you want to do planetary or asteroid exploration, you want to have some kind of plasma thruster or micro thruster. They talk about ion salt thrusters. They have fluid water thrusters. They use microwaves to heat up heavy elements and use that as thrust. It's kind of like a fan blowing on your hand. If you keep blowing that, you say, oh, let's back up. With a chemical rocket, you have a burn time, right? And then that burn time is a few minutes at most. You know, I don't know, maybe they could do longer now. But it only has so much time, that fuel's burned up, and then you get your momentum from that and you're off and going, right? But with a thruster like this, you can go for years with a little bitty fan. Well, what's going to happen if you're constantly accelerating over years? You get 200,000 miles an hour. Problem stopping. You know, you got this little fan trying to stop. But that's a real neat technology to read about. I've got a lot of stuff on my webpage, space-hobbies.com. How am I doing on time? Okay. So as other parts of our thing is communication systems. The only thing we have over them is we're adding LORA. Everybody heard of that long-range radio communication, LoRaWAN, and that's something, well, I forgot the kid's name. He's from Italy. He was 16 in 2016, okay? It's called FOSSA. And what it is, it's got this little, it's like they took a cake cutter and cut our 2U into 4 pieces and had one little section of it. What would you call that? A 1/4 something. Yeah, quarter U. But anyhow, he was going to put those up, and they're actually using these now. I think they're going to launch 80 this year is what they claim. First one was a failure, but that's often with these things. You throw them up there and they don't beep anymore. But anyhow, the little thing you made is this big, and they go up in orbit, and they can actually do things like find where your cattle are in the middle of Africa. You put a collar on your herd, and it'll beam up the GPS coordinates where you don't have to have internet. You don't have to have internet much of a bill. There's several different services out there, and they don't all use the LoRa protocol. We didn't bring one of those. No. You have one in there, but it's not active. So, but anyhow, it's a very slow, low range signal. It's well worth studying. It can go well below the noise floor, and that's what's amazing to me about it. Well, I think that's the end of my part, and he's going to tell you about LoRa. It goes way below the noise floor. It's not like Whisper. Let me take a second out. Does anybody know what time it is? 7:40. Okay, so you got 20 minutes. The balloons. How many people received a balloon repeater? Okay, I sent 20 of them out, so there must be some people missing. We're going to take groups of 5. We just got down here. I just got done with the trade show, just got down here. I've been trying to put it on the PCARS blog, you know, where we're at, messaging system. So after this, I had to get ready for this too, so I'm going to start calling you up and telling you when we're going to set up your Pico balloon. Those things are so cool. If you can't play with a CubeSat, the next best thing is a Pico balloon. How many people are familiar with Pico balloon? Raise your hands. Quite a few. They're little bitty transmitters this big, solar panels on them. We sent them up with a party balloon. It's $3. You may have heard about this though when the U.S. Air Force shot one down. Okay, $40 balloon. They shot it down with a $200,000 missile. Or was it $400,000 missile? Think of the house and swimming pool you could have for that one missile. You know, so you might have all heard of that. But that's what we send up. And there's a network of WhisperNet. Everybody heard of WhisperNet? Weak signal. And the reason that net exists is because hams want to know which way do I point my beam. And all these guys are tied to the internet. They have little weak transmitters that cost almost nothing. They send out a signal, and whoever receives them publishes it to Google Earth on the internet. And they draw lines from where you were to where they are. And eventually you see a bunch of lines. You say, hey, that's a good propagation path. I'll turn my beam that way. That's all it was for. But the Pico balloon guys said, well, wait a minute. We could just drop our signal down on those nets as we fly over these guys, and our balloon will have constant Earth coverage. And it does. Plus at that frequency and that bandwidth and that protocol, I think we're at 17 milliwatts, and I've gotten to Perth, Australia. You know, where I saw it going from the middle of the United States to Perth, Australia. So anyhow, I guess that's one protocol. LoRaWAN is a little more high-tech, math intensive. I think Whisper mostly works on low bandwidth, right? That's its big key, half a bit per, how slow is it? 1, 2 bits? Half a bit per second. So, okay, here comes Dan. By the way, we come from a company called Optical Wavelength Labs. We make test equipment for fiber optics. We've been doing that for how many years now? Lost track, 25?
Yeah,
30?
forever. Yeah.
I think 25, that's a good guess. Okay, so I've turned the show over to him, and he's going to give you a little insight to the LoRa WAN. LoRa, whatever it is. Thank you very much.
All right, thanks, Rob. Okay, so like Rob said, my name is Dan, and I'm KC9LGR, and I want to thank everybody for having us here tonight. We like doing this. Okay, there, is that better? Okay. So, and I'd like to welcome our guests. It's nice to see some fresh faces who are interested in this stuff. Rob pretty much covered everything about the PicoSats or about the CubeSats, except for we wanted to cover a little bit about the communication protocol that we wanted to use. Because these satellites are pretty low power, we wanted a communication protocol that would give us a decent data rate over a pretty big distance, a couple hundred kilometers. So there's not too many choices. Nobody here had heard of this before. No one heard of LoRa before? This is new to, okay, one person's, a couple people have heard of it. Yeah, I mean, everybody is familiar. Well, that's not, okay. Okay, so everybody's familiar with Wi-Fi, right, and Bluetooth, all those VHF protocols that we're used to for our normal day-to-day use on our computers. And of course, cellular, we're familiar with that. But there's another protocol that's beginning to be widely used for Internet of Things. Okay, so when you have sensors that aren't in your home, that might be further away, like farmers have things out in the fields or cattle they have to keep track of, remote sensors that are located way up in the mountains or strange places. Then there's another protocol available for that.
Or satellites.
Yeah, or satellites. So Wi-Fi covers higher bandwidth and shorter distances. Cellular is reliable in that if you want to have like a critical, mission critical type of communications where you have to have a response right away, then you pretty much want to have cellular or some satellite direct communications. LoRa it's reliable, but because there's not too many satellites up yet, it takes some delay time to get your results. So basically these stations will send data up to the satellite, then the satellite has to go over an Earth station where it can download the data. So there might be delay, several hours before you get the data. Go back. So LoRa's advantages, though, are it's very low power. These things can be operated off of solar. It's just one little IC chip. It's a digital transceiver chip. They're very inexpensive. We're talking only a couple dollars for the chip. You can get long range. It's basically line of sight because it's VHF. So on the ground, you can get about 10 kilometers. But for a satellite, you can get several hundred kilometers. It has an optimization in that it adjusts its data rate based on the distance. So it can basically throttle itself or speed itself up depending upon what you need for your particular mission. It has excellent noise immunity, and it has good indoor penetration. And like Rob said, there's many networks available that you can join. So here's kind of the scenario of how a LoRa network would work. So you have these remote sensors, like here's a crop sensor measuring water in the ground. So this sensor would know what the telemetry of the satellite. It knows when it's coming over. It transmits its data when the satellite is in view. And the satellite collects the data from that. And then when the satellite passes over like an Earth station, it downloads that into the cloud. So basically it uses the internet to collect your data. But then you use an application on your computer at home to access that internet on the data on the internet that the satellite has delivered. Okay, so that was the first use of LoRa, and this was pretty much used for now, except it's also used in some networks in communities where it's very rural and they don't have a lot of good access to other types of Wi-Fi networks. They'll use LoRa for like a messaging system instead of cell phones, and they can, message neighborhoods. And it's kind of growing in cities too, where they have mesh networks using LoRa as a kind of a bypass for the internet.
Again, just point out, it's kind of like DMRS for networking. Kind of similar mentality.
license,
Yeah, well, it can be used that way, right?
similar.
So there's two aspects to it. We're going to talk about the physical layer here, the protocol that's used to deliver this data. It's kind of unique. It's pretty interesting, I think, how they do it and how they get reliability where you can receive signals that are like 20 dB below the noise floor and still get reliable results. The upper layer stuff here, the MAC layer stuff, that has to do with more of the network you're a part of and how the data gets delivered. So we're not going to worry about that because there's a lot of these options. So down here, it's basically, it's a VHF radio. Oops, little typo there. And it's basically, they're open bands. In the US, it's 915 megahertz. In Europe, it's 433. You can also use it on the amateur band. This was developed by a company called Semtech. You can't see that there, but it's not MTech, it's Semtech. It's a proprietary protocol, but people have figured out how it actually works. Here's what the transceivers look like. They're very compact. This is about a 1-inch square. You can get them where they have actual microcontrollers that support a specific protocol. And that's what we're using in our satellite is a LoRa transceiver with a separate microcontroller. So you just talk to it via a serial port to send your data. It makes it real simple for the programmer.
Point out that just one of our transmitters, we have like 2 other ones that are repeater, and the other one is Raspberry Pi phase out.
Well, yeah, this is our third. This is the data transmitter that we want to eventually use because it's more realistic for long distance than what we have for the other two. So this would be a reliable data transmitter. And basically inside the IC, it's all digital, right? So we're using basically a DSP radio. We have this special LoRa modem that uses the LoRa protocol. It looks pretty much like any other receiver, except you have your low noise amplifier, comes into a mixer, and you immediately take the baseband signal and A to D convert it, so we're dealing immediately with digital data and all processing that happens there. The signal is generated via control of a phase lock loop here that will output our frequency modulation. And the way it works, and this is where we get to the interesting part, is it uses chirp modulation. So it's using chirp spread spectrum. So basically you either have an up chirp, where you start at a low frequency and go to a high frequency. And here's a frequency graph with time, so you can see we're going from low to high frequency, or a down chirp going from high to low with time. And the chirp rate, so basically a chirp rate greater than 0 means you're going up. Chirp rate less than 0 means you're going down. We won't do the math here. Now, remember I said it adjusts its speed for the distance you want to travel? So the way it works is you have a certain channel spectrum that you can work with, either 125 megahertz, 250, or 500 megahertz. And the way that channel is used is they can basically, the number of samples is always constant. So it's always our A to D converter, our phase lock loop, changing frequency is always happening at the sampling frequency. But the number of samples we use to send a bit of data or a set of data can vary. So let's just take a couple examples so you can see how it works. This thing called SF is called the spreading factor, and it's the number of bits that you send with each symbol that's sent. So we might be sending 7, 8, 9, 10, 11 bits at once with a symbol. So here, if I have a spreading factor of 11 right here, that means I'm sending 11 bits with each symbol. And if I go to the next spreading factor of 12, I'm sending 12 bits for this symbol. But you can see it's taking twice as long to send these 12 bits for this one as it did to send the 11 bits for this one. So that's what they mean by spreading factor. I'm sending 1 bit more data, but it's taking me twice as long to do it. But the advantage is now that I have a lot more samples that I'm sending, I can get a lot better resolution on my receiver. So I can detect the received signal much better. So it's a trade-off. Basically, I get better signal detection in longer distance with a bigger spreading factor, but I get lower data rate and I get a lot more power usage because I'm transmitting for a longer time. So here's some examples. Like with a spreading factor of 12, I can go at 293 bits per second, spreading factor is 6, I can go at almost 10,000. So you have a lot of variability, and you have a lot of variability in the receiver sensitivity here. It's almost 20 dB different from one to the other end. So it's adjustable. So we'd want to use something that we can get a good long distance on with our satellite. So we'd probably use like a spreading factor of 12. So here's how the data is sent. Each symbol is a chirp, right? So this is a change in frequency from low to high. And this is, the top of this here is the width of our bandwidth of our channel. So if this was a 125 megahertz channel, this would be 0, this would be 125, or I'm sorry, kilohertz. Another different symbol is sent with a different starting frequency, and the symbol wraps when it hits the top of the bandwidth of the channel and starts over at the bottom. So these are like 3 different symbols starting at different points, different frequencies. So the chirp is always wrapping at the top of the band and starting over at the bottom. Now the way the receiver works is it's going to have to compare a received signal, one of these chirps, to every single possible symbol that could have been sent. And that takes a long time. There's a lot of math involved to do the correlation to do that. And the neat thing about this protocol is that you don't have to do all that, because the way you correlate 2 different signals is you multiply by the complex conjugate of the signal that you received, or the signal you're comparing to. And it turns out that the complex conjugate of an up chirp is a down chirp. Okay, so if I multiply my received signal by a down chirp, I can remove the chirp altogether and end up with just one specific frequency or tone that relates to that symbol. So if I do that, I can end up with a much simpler signal that can be processed quickly. So here's my received signal coming in right here. Each different color is a different chirp that starts at a different frequency and wraps. Okay, this one starts at a different frequency and wraps. So when I multiply by these down chirps, what I end up with is just a specific frequency left over that corresponds to the value of the symbol. So this specific one here is for a spreading factor of 7, which means I have 7 bits are sent with each symbol. Okay, so I can have any value from 0 to 128. So for the first symbol here, when I multiply by the down chirp, I would get a frequency of 0. So that corresponds to the value of 0. Now these values don't exactly have to match the frequency, but each frequency has a specific value that it correlates to. So once you've done that, all you have to do is a fast Fourier transform of the data, and you can get the exact result quickly, and that's how these chips work. This is what a packet looks like. We have a bunch of up chirps that are the preamble. Basically, it's a way of synchronizing the receiver to the data. So what I'll see on my receiver, even if I'm out of sync with the transmitted data, I'll get a sequence of numbers that are all the same, so I'll know I'm at the beginning of a sequence of data packet. Then we'll get a couple of sync bytes that corresponds to the protocol you're using. So after you get these similar data points, you're going to look for 2 specific values here. When you see that, then they send a couple of down chirps, which decode differently. And basically that tells you that you're synced up with the data coming in later on.
We're running out of time.
Yep, the last slide. So here's what it looks like. Here's what that packet looks like. This is the packet that came in. After we multiply by down chirps, here's the spectrum of that batch of data. So you can see that each data bit in time here corresponds to a specific frequency. So these are the frequencies that were left over after we multiply by our down chirps. And each one of those corresponds to a 7-bit value in our packet. So I thought it's kind of interesting. It's a different technology. It's low power, and it's very useful for when you're going long distance and trying to send data. That's it for LoRa.
I got to finish up right here with a demo real quick. We'll pass this big satellite around, and we're just about running out of time. I'm hoping this demonstration works. I need the mouse real bad. Yeah. Okay, so what we have here, I think one of the points about this LoRa is that you can go, with these boxes, you can have simple Newtonian physics, or you can go up to the nth level of, graduate school electrical engineering, because that's what that was. Let me get over into this. I'm going to call up SDR sharp, and hopefully it works. Okay. wrong frequency. 3.9, 0. Oh, I'm the wrong item. I don't need this program. I need Foxtel M from AMSAT. And it's going to show telemetry coming across right now. And you know, we're trying to flashlight, which isn't, LED's not the right bandwidth to trigger the solar cells. This is coming live right now out of this CubeSat. Okay, what you're seeing is that housekeeping data and STEM data and other types of data. What I found out to make the satellite work is we'll just put it in front of the projector. That should give it plenty of light for the solar panels. Okay, yeah, so this is just the signal acquisition part of it, but if you go over here, here's the housekeeping. Now, if you look on some of these each one represents, well, some represent the power supply unit, the battery, experiments which aren't hooked up right now, X panel, Z panel, Y panel, plus and minus. And right now, I don't think anybody has any current, but I assume when you put that briefly in front of the, don't drop it. Problem is you won't be able to see it when it's in front of the projector.
Yeah, you can see it, but I can't.
Okay, well, I'll tell them how neat it looks.
Okay.
I think you'll be able to pull it away quick enough, you know what I'm saying, that they should see some change.
It takes a second to get.
Okay, I'll tell you which cell you're on. You'd think it'd be frying by now. I don't see anything. 0, 0, 0, 0. I don't understand that. That should be plenty bright. It works fine in the sun. Okay.
Yeah, I don't know. It depends on the wavelength.
Yeah, it could be the wrong,
Yeah.
something like that. Okay, that's an LED projector. It's probably got very narrow bandwidth each one. So we're going to pass this around. I'll put slow scan
Yeah.
up. How's that sound?
You can lift the hatches on the solar panels and look inside, see all the electronics.
If you don't want your face broadcast and don't look at the top, it'll probably give you a nostril
There's
shot.
one side has the muon detectors, and they probably have some numbers on there. Camera on top. I don't know if you did that, but
Have a display on something that's going to be orbiting the Earth and nobody can read it.
Because
So
it's
I-
educational and it's
it's
not really
modular.
going anywhere.
I take it off. It's the way I test it.
Yeah.
It's a diagnostic tool.
It looks
Yeah.
cool.
But
Come
when
on.
you launch it, you take that.
Yeah,
Yeah.
yeah.
It's a coolness factor. Okay, so we're going to do slow scan. And that should come in any second. It takes about a minute for it to warm up, the slow scan.
It's going to be moving though. People are looking at it.
Yeah, I know. But it does that one stock film.
That's noise. Yeah, that's noise.
That should be my call sign. Okay, waiting. There we go.
Yeah,
Okay,
it's,
here it
it's
comes.
sending a picture off the camera.
So if you,
right now,
if you look at the top, you'll see what your nostril looks like.
Actually, I think it's
Oh.
yeah, it's synced up.
Yeah, I noticed that. That's Scotty too. That's as good as you're gonna get around here right now, moving around. And,
That's just the demo image though. That's
well, it's
not
coming out of the unit though.
Yeah.
It does one demo
Oh,
unit.
then it'll do the
yeah, it
camera.
alternates
Oh,
between
okay.
that and whatever the ceiling's looking like.
Or wherever it's pointed at the
Yeah,
time. Yeah.
remember that, it's a big work in progress with that slow scan camera. But a lot of amateur satellites and university satellites use slow scan just like this, to use that magnetorquers and reaction wheels to tilt it towards the Earth so it's not just randomly taking pictures of anything. So I think there's a day coming with these micro thrusters that they're going to be able to leave orbit, you know, with this micro propulsion systems. And if you can leave orbit and you have really good navigation, because space is always changing. The moon's moving, we're moving around the sun, gravity field's always changing. But I think there's a way you can slowly take like 2 months to get out of orbit, get around the Lagrange zone, and you can actually get around the moon. And that, I'm sure they would laugh at Lance Ginner when he put Oscar 1 up, you know, but who knows what the next 20 years is going to bring. What I like to see is amateur rocketry mix up with this and launch our own satellites without the need of any, you know,
So
well,
should
they
be
still
the
make it,
picture.
have licensing. I'm sure you can't just shoot a missile out of your backyard. There is an area that you can do it. It's called Friends of Amateur Rocketry in the Mojave Desert, and they will let you launch very big rockets. And I think they're pushing to eventually get orbital. The Japanese have a rocket. It's called the SS-520. It's a solid rocket, and it can bring about a couple hundred kilograms to a 400-kilometer orbit. Now, you don't get a lot of good attitude control out of solid rocketry, you know, because it's one big ball rocket. But you can do something with it, and so that's something to keep an eye on. Oh, my slant is all goofed up. Well, that's because it's moving around. It's not my fault.
No.
Oh, if it was sitting still long enough, it would get the picture of the ceiling, but I'm doing a slant correction.
Don't break it, Bob.
So I guess that's, there we go.
There you
There's
go.
the ceiling. I think I see an official smoke detector or something.
No, a light. It's a light.
Is that what that is?
We got a light.
Yeah, that's what that dot is in the middle. It's coming in clear on my laptop, not so good on the projector. But anyhow, just showing you some of the demonstrations. I think this is a very good STEM thing. This kind of science and people getting into it, and the kids getting into it, family getting into it. I gotta turn that off. Just yakking away. It could really be a good activity for the whole family. Something to do in the basement with your dad or family or whoever's into ham radio. Remember, AMSAT's really a gem of ham radio. It's amateur satellites, but if there isn't a radio signal, they're lost, right? There is one exception. They have satellites now that are these university satellites. They're beaming down laser, just little tiny cheap lasers, and they're flashing Morse code down just because it's cool. Okay, that's our presentation. Oh, if you guys are interested, and we've given these out before, space hobbies. I don't have any specific thing planned yet because I just got down to Florida a little while ago. But if you want us to give a group or somebody, you have friends in that, get like 20 people together, free pizza. If you know from the past, I've given away free software-defined radios, and that was the good stuff, right? I'm looking at Phil, that's what he called it. So, they're about, with the connectors and adapters, they're about $40 a piece. Our company donates the money. Everyone that attends gets one free. And you get free pizzas, right?
Mm-hmm.
So you might want to sign up and create a thing, because we love doing this. I don't know why, but we do. Okay,
there you
thank you for hosting us, having us, whatever.
Pass to get the other section.
Microphone. Blow out this microphone.